Today we're going to be talking about automotive cooling. Typically what come to mind are radiators, but there are a lot of other types of coolers that fall underneath of automotive cooling. Transcoolers, AC condensers, intercoolers, and other auxiliary coolers that are mounted throughout your car. Now what we're going to be covering today is how they work, where they're located, and what you can do to improve them to make them more efficient. So let's start this off by talking about location. Where are these components typically found on almost every single car? And that answer is the front. The reason why these components are typically packaged in the front of your vehicle is because that is where the most fresh air is available. You're almost always guaranteed to have nice, clean, fresh air hitting the front of your vehicle in large quantities. Now there are some exceptions to this. Some vehicles have these things mounted on the rear. The engineers that designed them have created vents and swoops and a lot of things to kind of catch that air and bring it into those coolers and push it out the back. These things are almost always mounted perpendicular to the flow of air. There are a few cases in which packaging constraints are just so tight that engineers have developed ways to put the coolers in different orientations to help, again, grab as much clean, cool air as possible. Take, for example, the BMW M3. The oil cooler is mounted parallel to the ground. That's just due to the fact that there is not physically enough room up front for them to mount them parallel and stack them up together. When you stack multiple cores together, that's what's called a cooling stack. We have an example of a cooling stack here from a Supra. This is composed of a transmission cooler, the heat exchanger, which cools the air-to-water intercooler inside of the intake manifold, and a radiator behind it. Other vehicles might have an additional oil cooler here, or maybe an AC condenser in the front, and this is what basically does the bulk of the cooling on your vehicle. Now that we know where most of these things are located, let's talk about how they function. So you have to remember that whenever heat is inside of something, it's always going to flow from hot to cold. So what we have here is a core that has been cut open to demonstrate what happens internally on the rad. We're also going to talk a little bit about what happens externally. The way your typical radiator works is you have hot coolant that comes in one end tank. The coolant travels across the core and exits out through the other end tank. And at this side, it's cooled down. And when your coolant goes into your end tank, goes in through your inlet, goes down through the end tank, and is evenly distributed through the tubes inside of your rad. Now those tubes, they travel the entire length of the core itself to the outlet end tank. As the coolant progresses across the core, it is transferring heat into the aluminum of the tube from the coolant. Once that heat goes into the tube, it is then transferred to the fin, where it then exchanges the heat with the air that is moving through the radiator. As that coolant goes through the rest of the core, it is going to get progressively cooler until it reaches your end tank, where it is nice, fresh, cool coolant to go back into your engine to help take the heat back out again. It just keeps going around this big cycle over and over and over and over and over again. Now, the reason why most radiators are made out of aluminum is aluminum has a great thermal conductivity. It can transfer heat extremely well. There are other materials out there that do similar things, copper, brass, and if you know a little bit about radiator history, that used to be a really, really big thing were brass and copper radiators. The reasons why they're not used anymore, kind of twofold. Copper work hardens really, really quickly. So through multiple heat cycles, it will become weaker and weaker and weaker. Also doesn't handle stress really well. It's also expensive. Now, aluminum is relatively inexpensive, which is why they're typically made out of aluminum. And now we're going to dive into the different types of cores. Now, there are a lot of different types and they serve a lot of different purposes. So let's start out with one of the most basic, and again, we're going back to our cut open radiator here so we can see the inside of it. This is what's called a tube and fin construction. And this is going to be probably your most common for OE applications. So you have your tube, which is right here, and then your fin on top of it. And you can very easily see it if you look in the end tank here. You have a tube, which is either an extruded tube of aluminum or a piece of very, very, very thin material that's basically formed and then welded in this particular shape. These are what are called strutted tubes. So you see there's little struts on the inside here, little vertical braces. And those help to increase strength of this core, as well as prevent any sort of deflection as maybe some forces are transferred through the radiator if you're going over bumps or those sorts of things. Now these can be different diameters, they can be different lengths. In this case you have one tube, but there's some rads where you might have 2 or 3 tubes next to one another in a line. Now the fins themselves, they're on the outside and they are bonded to the tube by a process called brazing. Each one of these fins is a louvered fin, meaning that as you go through, there's actually louvers on the inside of the fins that deflect the air out to the side to help create turbulence and slow down the air as it goes through the radiator. Because if that air slows down and becomes more turbulent, it helps to take away more heat out of the system. So next on the list of cores that you'll more than likely see in your vehicle is something called a stacked plate core. Here's an example of a stacked plate core. They're commonly found in transmission coolers, and the way that they're constructed are every one of these layers is essentially a different piece. You can very clearly see that if we take a look at our cut open stacked plate here. So if we take a look here in the middle, you have your fin, which again is bonded to the bottom of one of these plates with the brazing process. In between, you can sometimes have fins. This particular one has fins inside the water or the coolant or the transmission passage. And then another plate is put on top of it to create the top half of that U profile. Then another fin is bonded to that, a plate, internal fin, top plate, fin, and just continues up through the whole thing. You stack them on top of one another. What we've done here is we've taken a rather beat up OE example. We've actually cut it in half along the top plate, the bottom plate. So the bottom plate, you can see the internal fins here, and then there's the top plate. And the way that those would go is they're bonded together like this. One of the really big advantages to this is, one, you can actually have fins on the inside. So this helps to turbulate whatever fluid may be running through the inside of this cooler, and again, that helps create better heat transfer. But the second thing is, these are incredibly durable. You can run a lot of high pressure with this, and the stacked plates themselves have a thicker wall thickness, making them much more resilient to things like stones or rocks or any sort of road debris that you might come across. So while a stacked plate core is extremely durable, there's one that's even more durable than that, and that is bar and plate. These are typically used on intercoolers, especially in the aftermarket segment where we're replacing a tube and fin style intercooler core, which is what the OEs typically use with one of these. These are also seen in extremely heavy construction equipment. So things like skid loaders and backhoes, they typically use these as radiators, oil coolers, and even intercoolers. They're usually kind of all built into one giant unit. The reason why these things are so strong is just due down to their construction. We've taken the time to cut one of these things in half because they are kind of tricky to understand. So this is a cross section of a bar and plate intercooler. Now what you have here is an external fin. There's a thin 1/2 millimeter plate that is brazed to a bar that is then brazed to another plate that is then brazed to a fin. So essentially it's almost like you're building like a Lincoln log style house all the way up through this entire thing. And the reason why this is so strong is just simply due to the fact that the plate and the bar, there is a very large amount of surface area that's connecting those two things together. The brazing process is what's holding that together. So when this thing sees an impact or a deflection, there's a lot of material here that is essentially able to withstand that impact or prevent that deflection. One thing with these two, you can run a lot higher internal pressures with this than you can stacked plate, than you can with a traditional tube and fin. So if you're turning up your boost, this is going to help you prevent blowing out an intercooler core. And with the welded end tanks that are usually cast, at least from Mishimoto, you're going to make sure that you're not going to blow out that seam that is just a simple crimp and gasket on an OE style intercooler. So the last type of cooler is a liquid to liquid cooler. Now the way that this works is it's a series of stacked plates with fins on the inside of them. So it's very much the same as this one here, but instead of using air on the outside of it, it uses a coolant and either an oil or transmission fluid. These are typically seen bolted onto the side of your engine for an oil cooler or bolted onto the side of your transmission for a transmission cooler. The reason why these are so effective is they're very small. This particular core size here has a very, very large amount of cooling, whereas this has a large amount of cooling, but it's also much bigger than this. And with a lot of new vehicles, inside your engine bay, there's not a lot of space. So what the OEs do is they put one of these on here. One of the downsides to this is that it does use your engine coolant in order to cool the oil or the transmission fluid. But the flip side of that is if you live in an area where it gets extremely cold, it works in a reverse way. It works in a way to heat that fluid to get it up to its optimal operating temperature faster, so that way you don't destroy your engine because your oil is really, really thick or your transmission fluid isn't flowing easily throughout the transmission. This particular technology has also been adapted and kind of working in a way with air-to-water intercoolers as well. So if you have an intercooler on a newer vehicle that doesn't have your typical front mount, it actually is just a unit that's bolted to the intake, it's using a very similar construction design here. So this brings us to the question is, how much cooling do you need and when do you need to start making upgrades? Well, a couple of really quick things would be if you have a turbocharged car and you start running more boost, you're going to need to start improving your intercooler. And if you have a big truck and you start taking it off-road, you're also going to need to start improving some of those systems like a radiator and possibly a transcooler. So how do we improve core performance? Well, there's a couple different ways to do this. By far the most effective, but probably the hardest way, is to increase frontal surface area. Now that just means that we take this surface that you can see here and we would make it bigger. So we would add height to the rad and we would add length to the radiator. What that's going to do is it's going to allow us to put more tubes and more fins inside of here, which is going to give us more ability to reject the heat out of the system. Now there's a problem with that. You can't just make this thing giant because it has to fit in a small package. So most of the time, the OEs have designed a rad that basically maximizes the amount of space that's in there. So we're left with other ways that we have to, use to create better cooling efficiency. So one of those ways to increase efficiency when you can't make the front bigger is to dive in and take a look at the tubes and the fins themselves. So typically OEs, they're getting better recently, but they used to use really tall tubes with really tall fins. Well, what you can do is if you make that tube a little bit thinner, you can fit more tubes in this surface area. If you make the fin height smaller as well, you can also fit more fins inside of here. And every single time you do that, you're effectively giving a greater ability to reject heat out of the cooling system. Now, with a smaller tube, it also gives a smaller area of fluid to go through. So you could potentially increase the pressure, but it's nothing that's drastic. That smaller area of fluid also makes it easier to cool that fluid since there is less fluid inside of that one small tube. The fin heights also get tricky. You could pack the fins and make them 1 millimeter tall, but then you're really not going to get a lot of good air going through the core itself. So you can't make the fins too small or else you won't get air going through it, but if you make them too big, you leave margin on the table to help reject more heat. And the last thing is something called fin pitch. Fins come together in a point and they're just a series of points. The pitch is the distance between the top of one and the top of the other one. If you make that tighter, you can effectively pack more fins inside of one row, but again, if you make it too tight, you run the risk of choking out air and not allowing air to get through the core, which is just as bad as having fins that have too large of a fin pitch. So one example of where we've really tailored a design to meet a specific application is with the BMW F80 heat exchanger. And what we did there was the lower eighth of the heat exchanger itself sits in front of a DCT cooler. Now, if we were to take that same fin pitch and everything and run it all the way down the entire core, there is a chance that we're going to block a good amount of nice, fresh, clean air from hitting the DCT cooler behind it. So what we ended up doing was on the lower portion of the rad, we made the fin height taller and the fin pitch wider. So that allowed more air on the lower section to get through the heat exchanger and touch a DCT cooler without creating any sort of issues with the DCT coolers down the road. But what that allowed us to do was make the frontal surface area longer, since the stock heat exchanger did not cover up the DCT cooler, and we made ours longer. So what we were able to do there was achieve two of the really big bullet points when you're upgrading your rad, or in this case a heat exchanger: frontal surface area and fin area. We were able to make those basically as large as we possibly could and made a huge substantial gain over the stock one. So one of the next ways to increase performance is to make the rad thicker itself. So that's taking this dimension and making it larger. It's probably one of the easiest as far as a geometry standpoint goes, whereas if you were to try and make the frontal surface area bigger, you run into the risk of actually running into things. Whereas going front and back, making it thicker, there's really not a whole lot in front or behind the rad that's going to limit that space. Now, there is a point at diminishing returns with this as well. There is an effectiveness at which you make this too thick, and then you can no longer get heat out of the system. So you've kind of already soaked up as much heat as possible. That's really dependent on your fins and your tube geometry. So once your rad has soaked up the maximum amount of heat, it doesn't matter how thick you make it, you're not going to take any more heat out of that system. So you can't make it too thick, because again, it's going to prevent airflow, but you don't want to make it too thin either, because you could be leaving a lot of gains on the table. When you're taking the time to optimize things like tube height, fin pitch, and the thickness of the radiator, you end up with more fins, and that gives you more fin surface area, which creates better cooling optimization. So let's take a look at something, a practical example, here on our super transcooler. So here's the stock unit, here's the Mishimoto unit. What we managed to do with this was we made it thicker, so that increased the fin surface area in that direction, meaning that the fins are now longer, so they have a little bit more surface area. But we also created a larger frontal surface area. So that larger frontal surface area also gave us the ability to put more fins in here, which again increases that fin surface area. What we have here is a calculated fin surface area for the stock Supra transmission cooler. We compared that to the calculated fin surface area for the Mishimoto. So what this easily demonstrates is how much more fin surface area you can get by simply increasing the frontal surface area and the thickness of your core. Another way to get performance is to actually change the flow parameters of the coolant completely on your rad. And that means going from something called a single pass to maybe a dual, triple, or quadruple pass, if you will. Now, how do you do that? Well, we've actually already described single pass earlier. And right here in front of me is a rad from an MK7 that we're designing, and this is a single pass design. But we were curious. We wanted to see if there are performance gains to be had if you did a triple pass. So here's a rad that we made that is a triple pass design. What you have here is a baffle that's been welded in here. This baffle is just a plate that goes across the end tank. What happens is, as the coolant comes in the inlet, it goes down into the tank and it hits this baffle and it can't go any further down. So it then goes across the core. Into this end tank, it makes the turn and goes down until it hits another baffle. Once it hits that, it goes, oh, I can't go down here. So then it goes back across the core this direction. Once it goes across this direction, it goes down to the very bottom of the core, and then it goes across and out through the outlet here. So it makes 3 passes across the core before it leaves. The idea behind this is you basically are now effectively only having to cool a lot smaller area of coolant. It also creates a larger pressure drop in the core, meaning the coolant thus moves slower through the core. As it moves slower, there's more time for it to exchange heat with the air that's moving through the core itself. Now, we tested this on the MK7. We tested this against our single pass. Both have the same core design, so the same fin height, fin pitches, and tubes. And a single pass performed just the same as this triple pass did. Now, that was that particular instance. There are some instances where a triple pass does perform better, but in this particular case with Radiator, we didn't see any big improvements on it. So the takeaway from that is, it's not always about how many times the coolant passes the core. What it really boils down to is the fin heights and the fin pitches. So the last way and the least effective way to increase cooling performance is to increase cooling capacity. That means by making end tanks a lot larger, but more times than not, it's somebody adding a reservoir of cooling somewhere inside of their engine bay or maybe even in their trunk. The problem with that is, while you are making it take a lot longer for your vehicle to overheat, you're also making it take longer to cool down because there's more fluid inside the system. But because you're not changing any way at which that coolant interacts with the environment around it, there's no fundamental way that you can really say that you are increasing the efficiency of your system. You're just delaying the onset of a potential problem. So one quick example where this might actually be helpful is if you're using your vehicle as a drag car, where you're blasting down the strip and then you sit in the pits and you notice, hey, my car's actually overheating. Well, because you're not running your car that long, or you're not really going around a track, you're not going for lap times, it might make sense for you to add a little bit of cooling capacity to delay that onset of overheating. That way you might be able to get more runs at the drag strip without pulling your car into the pits and letting it cool down. So the key takeaway from all of this are, there is a lot of different variables at play when it comes to upgrading your radiator, intercooler, transcooler, whatever it may be. Whether that's the location, how much fresh air is hitting it, or the fin height, tube height, the surface area, the thickness, all of those things are going to play some sort of effect in how that core performs. Now, one thing that we do here, and we really pride ourselves on, is the amount of testing that we put into our products. We test multiple cores against one another. We test different flow characteristics, such as triple pass and single pass. We test different fin heights, tube heights. We test bar and plate against tube and fin intercoolers. We do all of that stuff here, either on our dyno, out on the road, the racetrack, just to ensure that we are providing the best possible product for the best situation.